Hi everybody. Actually, before I get to the other methods that I mentioned, I want to do a case study and how you can use the Taylor expansion to do an error analysis of one of these methods. So I'm going to do the trapezoidal method, and I'm going to apply Taylor's expansion, Taylor's series, to do the error analysis and get an asymptotic error formula. Let's see. First of all, what we're going to assume is that y of x, capital Y of x, that's the true solution to the ODE that we're working on. And then y is just a function of x. So we can expand y in an ordinary Taylor series. So here I'm doing it an order 2 Taylor series. Right? So it's equal to, I'm expanding it about the point xn. So I'm assuming xn is the nth point we're going to try to calculate the solution for. But this is the true value of the solution at the point xn. It's capital Y of xn. And then we take the derivative at that point times x minus xn. And then the second derivative divided by 2 times x minus xn squared. And then at the end we've got this error term, which is, is expressed in terms of the third derivative of y, evaluated at some point c between xn and x. Right? Okay. So now we're going to combine this Taylor formula with the fact that y prime is equal to f, right? In the ODE, y prime is given by the function f. And so if we have the exact solution, then y prime will be simply equal to f of x, y of x, right, evaluated at the point of the solution y. Now, from this fact that y prime equals f, we can calculate the second derivative of y in terms of f, right? This is just a simple exercise in doing partial derivatives and computing the complete derivative of something. I actually carried out in more detail over here. So I'm saying that we want to take the derivative with respect to x of f of x, where we treat y here as if it were a function of x. Right? So y represents the true solution, so y itself is a function of x. Of course, x is the independent variable. You may remember this scheme from Calc 310, Calc 3, that to get the total derivative, you differentiate, you take each partial derivative of f and then multiply each partial derivative by the corresponding ordinary derivative. So if we want to differentiate with respect to x, we first differentiate f with respect to x and then multiply by the derivative of x with respect to itself, right? Because the input here is x. Of course, this term is just 1. So that's going to disappear. And this is what I've been writing as f sub x. Right? Over here, we take the partial derivative of f with respect to y, and then we differentiate y with respect to x to get this. And so this is what I've been writing as fy, whereas dy dx, that is just y prime, right? That's just what y prime means. So plugging that in, we can say that that y double prime is equal to f sub x plus f sub y times y prime. And by the way, since y prime is equal to f, we could even write it like this. We could write it entirely in terms of f sub x plus f sub y times f. Okay, now I'm going to plug this in for y double prime up here. Right? So I'm going to plug this expression. Let's see, I'm going to plug this expression in for y double prime up here. And then, so what do we get? Let's see. Oh, also, we're going to evaluate this at the point, I'm going to rewrite x here. I'm going to rewrite x as xn plus h. And that means that x minus xn will just be equal to h. So wherever you see x minus xn, we'll replace those by h's. Wherever you see x, xn will still be xn, of course. Okay. So if we want to apply the Taylor expansion to the value of y at the next x point at x sub n plus 1, well, x sub n plus 1 is exactly xn plus h. So we simply make that substitution, h for x minus xn. So we get the same first term. This term here simply becomes f times h, because y prime is equal to f, and this is h. The second term, we got a 1/2 here, we got y double prime. So for y double prime, we'll plug in that formula that we just came up with over here, right? And we've got the 1/2, and then this we replace by h squared. And then finally we've got this third order term, and I'm just going to write that as, you know, it's a term that's of order 3 in h, right? So it's order of h cubed. And I'm not writing out exactly where I'm evaluating f, but all these f expressions, f, fx, fy, they're all evaluated at the previous point, xn, y of xn. Okay? Now, so let's see. So here I just copied that same formula from before over here, right? And, oops, and wait a minute, I'm lost. Oh, there we go. Okay. And then here's the thing to notice is that this part of the expression, right? This is our calculation for the true value of y at the next x point, right? And if you look at this, there'll be propagated error in our calculation because we will not have the correct value of y at xn, right? So that means whenever we evaluate these f's, fx, fy, we're going to be plugging in the wrong value for yn. We won't have the exact value. We'll have an approximation. So that means that, oops, I did it again. This whole term here, or these three terms here, represent the propagated error. They're the terms that we will not be able to calculate exactly when we're doing our numerical calculation. So that's where the propagated error will come from. Right? Inherited error because our previous value of y was wrong. And then this will be the truncation error because no Taylor series, no second order Taylor series could give us the exact value, so we're always going to be working with an approximation. This represents the error that's introduced at the n plus first step, because we can't compute the exact value of y sub n plus 1 just using the two-term Taylor series. Okay, so we've broken the error that we've got up into a propagated error that represents our our error in evaluating this term, and the truncation error here. Okay. Now, recall that the truncation error determines the rate of convergence, right? Because if you've established, for example, that the truncation error is of order h squared, as we did with the Euler formula, then we know that that'll result in an overall error of order of h, 1 degree lower, and that's because the propagated error will just continue to be on the same order as the previous propagated error from the previous step. So here's what we want to do. We want to show that in the trapezoidal method, that the trapezoidal method actually will match these terms, and it'll leave only this error of order h cubed, and that therefore in the trapezoidal error, the truncation error will be exactly of this order of h cubed, and therefore we'll be able to show that the trapezoidal method, the overall error is 1 degree less. It's of order h squared. Okay. Now we have to do one more application of Taylor's formula. Here I'm applying Taylor's formula to a function of two variables. You may not have seen this in 310. I don't know. Maybe did they do it in 311? I'm not sure. I'm sorry. I should be saying 311 and 312, not 310 and 311. So you may not have done this in 311, but they may do it in 312. I'm not sure. But basically it's the same idea. This is just the first order approximation. What we say is f of x plus epsilon comma y plus eta, that's not an h by the way, that's actually an eta, So f of x plus epsilon, y plus eta. So we've moved a little bit from our starting point. So we start off with the value at the starting point, xy, right? Take the value of f there. And then we say, well, look, we moved a little bit in the x direction. The amount we moved in the x direction is epsilon, so we multiply by the partial derivative of f with respect to x. And that gives us, that will give us an estimate for how much f has changed due to the movement in the x direction, and then we do the same thing for the movement in the y direction, right? Movement in the y direction was eta, we multiply by f sub y. And then the error term left over is going to be of the order of epsilon times eta. So it'll be a second order term, right? Epsilon times eta, we're assuming these are small quantities. Okay, so this is the linear Taylor expansion for a function of two variables. Now what we're going to do is apply this to the trapezoid method. And first of all, let me apply it in the particular case where we want to evaluate f at a point nearby to a point that we know, right? So I'm assuming that we know the value value of f at the point xy, and so I'm going to replace epsilon by h. Right, that's what you normally do. If we're at the point xn, we're going to want to go to xn plus 1, which corresponds to adding h to the x value. And we're going to change y by hf. So hf will correspond to eta. This comes from the fact that f, remember, is our value for y prime. And so if we multiply h times f, we get an estimate of the change in y. Right? And in fact, this is what we'll use in the trapezoidal method with only one iteration to solve the implicit equation. I'll go through that in detail in a second. But this is going to be our change in y. It's going to be h times f. So plugging that all in, what we get is f of xh. I'm just going to write that as f. Right? Everything is evaluated at xy. Then epsilon times fx, well, that just becomes h times fx. Eta times fy becomes hf times fy, and then we've got this order of h squared term because epsilon is h and eta is hf. That's h squared times f, so that's something that's going to be on the order of h squared. Right? So I'm just going to write that this way. Okay, now let's look in more detail at the trapezoidal method. So what we're going to do is we're going to define yn plus 1 to be equal to yn plus h times 1/2, or in other words, the average of the two values of f we get. First, we evaluated at the previous point at xn, yn, and then what we do is we simply evaluate it at our estimate for where the next point is going to be. Right? Now, what this corresponds to is, what we're doing here is I'm taking yn plus h times f. Notice this is exactly what you do with the forward Euler formula. You'd simply guess that the next yn plus 1 is simply equal to yn plus h times f. Right? Here, we're not being quite that naive, but we are using this as our estimate for the y value to plug in for as the second point where we evaluate f. So, another way to look at this is that we're doing the iteration method where we try to solve this equation for yn plus 1 iteratively by taking each estimate, plugging it back in, but here we're only plugging in our first estimate for yn, plugging it in, and then we immediately cease iteration after doing the first iteration, right? And then we're content with the estimate that we got after the first iteration. And you'll see this is actually good enough. It's actually good enough to give us the result that we want for the speed at which the trapezoidal method converges. Okay, so now what I have to do is I have to plug in for this, I have to plug in the expression we had on the previous page. I actually copied that over here. So this expression in the blue box becomes this. F of this I'll just write as f. We got h over 2. Okay, plug everything in. So the yn, let's see, so we get yn plus 1 equals yn. Now we're going to pick up h over 2 times f here. We're also going to pick up another h over 2f from this term, because this term here contains a factor of f, which gets multiplied by h over 2. adding up those two terms, h over 2 times f, we get simply h over f, and the 2's cancel. Okay, so we get one term like that. And then we've got, let's see, this h times this h, and this h gives us an h squared over 2. Right? The h over 2 times the h is here, h squared over 2, and times the fx plus ffy, which, as we saw, that's exactly y double prime. So what we've got here is we've got essentially the first term, the constant term, the linear term, and the quadratic term from the Taylor expansion for the solution y that we wrote out a few pages ago. So remember, so these match essentially exactly. The difference is that, of course, these are the exact values and these are the approximations, but the difference between the two terms will simply be the propagated error. So we've essentially matched by using the trapezoidal method, we've actually got this term, and this is exactly the same propagated error that we discussed earlier, because we won't have the exact y values to plug in. So that means that the truncation error is the same as it was in the earlier equation. It's going to be of order 3. Because the truncation error is of order 3, of the order of h cubed, that means the overall error in the trapezoidal method will be 1 degree less. It'll be order 2. And so this verifies that the error in the trapezoidal method, even if you only use this very simple method to get yn, we simply do one iteration, that's enough for the convergence to be of order 2. So it's a whole order faster than the convergence of the Euler method. Whether you use the forward or backward Euler method, it was just order 1. So this is a much faster convergence. Notice also, in the MATLAB function we used the other day, we were doing up to 10 iterations in order to solve the implicit equation for yn plus 1. It turns out you really only have to do one iteration, and it works essentially as well, or at least as far as the order of the convergence, it's still order 2. So this is a much this should be a much faster method than using the forward or backward Euler methods. Okay. One other thing that's worth pointing out. So now that we have the we know that the trapezoidal method converges with order h squared, right? That the error is of order h squared. We can apply the Richardson error estimate that we've used in various guises. In this case, so according to what we just learned, the error in a particular y value that we get is proportional to, let's see, is proportional to h squared. So k is just some constant here. And this is an approximate equality, but it should be true asymptotically, right? So as h gets smaller, this should approach exactness. And then if we do a more accurate estimate for y using h over 2 instead of h, then the error should be proportional to h over 2 squared, or h squared over 4. And now using these two approximate equalities, multiplying the second one by 4, we see that the right sides are equal. So we can set this side equal to 4 times this side, right? So that's what we have here. And then there are two ways you can solve this. You can either solve for y to get just get an immediately better estimate for what the true value of y should be. And it turns out you get 4 times the better estimate, y using h over 2, minus the previous estimate, y using h, divided by 3. And again, this is like weighting the two estimates. You weight the new estimate 4 times, you weight the old estimate -1 time, and then divide by 3. Or you can also calculate y minus yh2, in other words, estimate the error with the improved estimate of y, and then you get the new estimate minus the old estimate divided by 3. So that's Richardson's error estimate.